Okay, so now we are going to go over the compilation of NRLMOL. That is, converting the Fortran source files into a binary program that can be used to run actual calculations. Okay, so first of all, in your directory, there should be a file called makefile. Okay, capital M though. And this file will be executed by just running the command make. In this case, it's all lowercase. Okay, so if that file is called differently than just makefile, then you execute it with make -f and the name of the other makefile. Let me open my source code directory here, and I have the directory where I have all the source code. And in here, you can see all the F and FTM files and F90 files that are the actual source code for NRLMOL. Now, let me scroll up a little bit here, and you can see that there's the file called makefile. And there's other like makefile hopper, makefile.lonestar, makefile.luit. Those will have to execute it that way, make -f and then the name of the other makefile. If it's just makefile, you just type make. So let me just type make here, and it starts compiling. Okay, so let's let that run its course and go back to the slides. Now, this makefile, of course, performs several tasks. It builds the application by compiling all the source files. It puts them all together, or links them, as we say, into a single binary that can be executed. It also used to clean the code. That is, for every file compiled, there's an equivalent .o file that is created, and sometimes we need to remove those. So you do type make clean or make -f if you have some other makefile, and then clean. Okay. There's also a section that defines code extraction. Okay, that's done through the comp program, which is the first file that's actually compiled, and that one will extract either serial or parallel executions of NRLMOL. We'll cover this shortly in a minute. Okay, now compilation. The compilation of the source code means that for every Fortran file that there is, you define the subroutine name, you define integers or reals, different types of variables, then you do operations with them. They are converted into binary code, okay, which is now machine executable. That works fine if it's only a single source code, but however, when you have several source codes, then you have to put them all together in a process called linking. Okay, so you're going to take all these source files that have been compiled into O file, object files, and you link them together along with external libraries, which can be mathematical libraries sometimes provided by the compiler of the system you'll be working on, and they're going to be put together into a single file called NRLMOL_exe, or in older versions of NRLMOL it's actually called cluster. Okay. Now, some considerations to take when you're compiling the code is you have to make sure that you're using the correct compilers in the system where you're logged in. That is, sometimes remote clusters can provide several types of compilers for different companies, and those options for those compilers have to be set in the makefile. Okay, there's also compilation and leak flags that must be set for those compilers in particular. Okay, make sure also that you're either compiling for the serial or the parallel executions of NRLMOL, and that you use the linking options depending on the system again where you are logged in. Again, this goes for the external libraries or mathematical libraries that can be fine-tuned by the company provider for better executions. Okay. Now, there's also in the source code directory a file called params. Okay. This file just specifies the sizes of different static arrays that the program uses. If these values are incorrect for depending on the system that you're running or the molecular structure that you're running, then the code will probably stop. Okay, it will suggest at the end of the output a new value for the parameter that must be changed. So therefore, you have to go back and remove the O files, the compiled files, change the value to the correct size specified for the parameter in the params file, and you have to recompile the code. That is, you have to run make again. Okay, this process can go on for several occasions, so you may have to recompile the code several times. And these values cannot be extremely high because the bigger the values, the more memory they take. So eventually you'll reach a limit where it doesn't longer compile. That's usually for large systems. Okay. Here's an example of this. There's a parameter called mx_cnt, max count, which is the number of atoms of the structure being calculated. And you can store up to 10 atoms in this case. If I'm running this complex that's actually 22 atoms in length, then it's not gonna fit. You can only fit 10 atoms on there. So the program, again, when you're executing, it will stop. It will tell you to change max count to 22. So you have to go back to the source code. You have to change the value in params, clean the code, and recompile. Okay, we will do this shortly on the screen. Okay. Now, the comp program, okay, as I said, it extracts either the serial or parallel compilation for executions of either serial or parallel of NRLMOL. Nowadays, we also use it for other special runs, which is using the Scalapack driver for parallel diagonalizations. This is done only for large system under certain conditions, and it also configures the code for calculations that we call groups. This is mainly done in bidirectional calculations. Okay. Now, the code extraction works this way. Let's suppose you have a file called code1.ftn. In there, you specify different code sections that will be executed depending on the environment variable that is set upon compilation time. If you use the DMPI variable when you compile, then when the code is being compiled, then A will be equal to 2, then you go into this section where you define MPI, so B takes a value of 3, and then you take C equal to A plus B. So, therefore, the new source code that will be created will contain those instructions that were done based on the definition if the MPI is defined or not. Okay, if you don't, then you go to this part. Okay, so this code is now extracted into this file called one.f. Either case, both files will be compiled into a single object file, and afterwards they will be both destroyed. So you're left with the original source code, the FTM file that contains, both definitions, whether it's defined or not. Okay. So in the end result, when you compile, once this process is finished, you will have a new file called NRLMOL_exe. How can we check this? Well, you do ls-ltr on the directory, so it should be the last file that is listed there. Other names may be called cluster or cluster.opt. Okay, this file, the NRLMOL_exe file, the green file that is created in color green, must be moved to the directory where you will be performing your calculations. And of course, it's suggested you never actually run a calculation in a directory where the source code is, because NRLMOL creates a lot of files, so it'll just be the directory will just be cluttered. Okay, so let's now go back to the terminal where, as I said, the compilation is finished. So let's do this again. I do ls-ltr, and as I said, since we left this compiling while we were giving the presentation, you can see a lot of O files being listed, and at the end we have the NRLMOL_exe. That's green, therefore look at the attributes, it's an actually executable file. Okay, if I just do ls, then you can see that for every F file there is a corresponding object file. That means that every F file was converted into or compiled actually into an O file, and they were all linked together to produce the NRLMOL_exe. Now let's suppose I have to make a couple of changes. I need to make now this a spin polarized calculation, so therefore I would have to modify the file called params, and in there I will change the value of max spin to set a spin of 2. Okay, so I save and exit using VI, and I need to recompile the code because those O files that are there were compiled with the previous params. So in this case, I would have to go and make clean. That cleans the whole code, and I will have to make to recompile a new NRLMOL_exe. If I do ls now, you can see that the NRLMOL_exe file is actually gone, and all those O files are also gone. Okay, so let's suppose now I have to make another change. I now want to compile the parallel execution of NRLMOL. So I open the make file. Okay, and these are the linking options. So let me go up a little bit until I have the compilation options. Actually, it's already set to the MPI calculus. Okay, so let's say we want to do the serial compilation. Okay, compiling this for executing on a single processor. Then all I have to do is just put a pound sign in front of it, so this comments out the MPI version, and take the comment off for the serial version. So this will compile now the serial execution of NRLMOL, or a serial version of NRLMOL. I save and exit and type make. So this goes through the compilation process. You can probably see that the comp program is running, so it's extracting the serial part because DMPI is no longer defined. So this is just extracting the serial code. for the NRLMOL execution. The compilation finishes, and I do ls -ltr, and you can actually see that the last file listed is NRLMOL.exe. You can now take this file into the directory where you're going to run calculations. All those old files there, you can keep them there. You can remove them by doing make clean. Okay, this